In this application, what we're doing is we're actually encouraging students to understand eigenvalues and eigenvectors by looking at things geometrically in addition to algebraically. In this particular case, we're starting out with a matrix ABCD in R2, and we're going to look at it graphically, and then we're going to come back and look at what goes on from an eigenvalue eigenvector standpoint, letting the computer algebra system itself do the calculations. So suppose we start over here. The matrix is actually tied to these four matrix entries, A, B, C, D, so that I can actually click on these values and toggle them. This gives students the ability to manipulate the matrix in addition to the vectors so that they can change the matrix and see what happens. Down here I have a unit vector. I've placed a dashed line on the unit vector so that we can kind of see the alignment of the vector more easily. Here I have the actual coordinates of that unit vector, and then here I have a transformed vector that's transformed by the matrix ABCD. I can actually take the unit vector now and pull it and watch the transformed vector move as I do it. And the question is, when do these line up? When is the transformed vector simply a scalar multiple of the original unit vector? And as you can see, if I go to here, I get a value of about 1, 0 for within rounding. And the length of my new vector is 2, roughly, within rounding. If I grab this now, I can pull it and say, okay, can I make it do it again? Can I make it line up? Well, in this case, I can make it line up. However, it's in the opposite direction. So the length is about 1, and the vector is about negative 0.321 and 0.947. Now if I pop back over to the realm of the computer algebra system, I can do the calculations for eigenvalues and eigenvectors. So suppose I want to do the eigenvectors. And I grab my matrix. This matrix is now tied to the matrix that's on the other page, indicated by the fact that these are bold-faced looking letters. And there are my eigenvectors, 1, 0, and negative 3.16 and 0.948, approximately the same as what I got over here. And if I want to look at the eigenvalues, I can do the same thing. And there are my eigenvalues of 2 and negative 1 corresponding to the lengths that I received of my transform vector when I move. There's the 2. There's the negative 1, negative being in the opposite direction.